This is still part of the session.
Yeah, there's a lot of
these are
people
the
on here.
topics. Do you want to
This one until 3:30.
call by one and then like Okay, so we have about 25 minutes, and then we talked a lot about white papers, and then we are grassroots effort, but we listed a few topics here, and then actually some of the topics that listed here. Alex, could you go to the kind of top of random list on the top? Well, okay, so there's something like a consistent picture. So this is a mixture of topics that raised within this workshop, the Grand Challenge session from last year, CEDAR Workshop, and then this year. And then some of the things that came up, for example, last year and this year, hemispheric asymmetries, for example. And then the other one that the last speaker talked about how to sort of track back where it's coming from, this pointing flux, alphabenic scales, and then bursts, and then all the response that really is IT response and the way it's tracked down, and then scale distributions. So there are lots of subtopics. And then, as you may have heard, that it's good to have a few papers on the topic. And then there's GDC, and then maybe dynamic data or other, the Lotus mission. Maybe some of those things that we should, I don't know what is the strategy, but I think in a town hall meeting, we discussed that maybe working to make our pie bigger, so maybe rather than GDC versus dynamic or Lotus mission, maybe we can really highlight importance of science, that we need all the data, and we have a very important question to address. And then I know this is a grassroots effort, but those are the topics that we collected, and it came from many of you in this room. So I know we are all busy, but if you could put your name. So this, Alex, link is in our, could you navigate to show the link? You can see his name. So it's go to our Grand Challenge website agenda. So go to the agenda, then find this workshop Tuesday afternoon. We had a morning session as well. There you go. So then there's a Google document. So it's you should be able to edit, and then really interesting talks. Aaron came up, and then it's true that we all have to measure all the things together. It's not just E and B. Maybe we want to have it at multiple altitudes, and then we need to measure particles to understand the IT response. So there's a lot of topics there, and it's not just we need multiple data, and then we have very exciting mission plans coming up. So we really want to facilitate the process so that we have better chance that we can have some closure on this important topic. So could you please? So let's go so let's go from top. So who you might feel, so these are not exclusive topics, and maybe some of the topics might be combined. And then if you have some papers that you wrote 20 years ago, or maybe you're writing right now, maybe you could volunteer and then show us. Maybe it's not that we're gonna go after you, but it's nice to have some documents that, oh, okay, so I can contact this person, so that we have something so that we can work on, build on some momentum. So how about this, the first topic, how to link pointing flux measurements at the real altitudes to IT response on different scales, and then all kinds of things. But this seems like some of the things that it's measuring pointing flux is one thing. The connecting dots to the response, I think some of you feel maybe feel like you want to sort of, as a cohort, you could put your name there or volunteer. Maybe. To that. Yeah.
You might say, well, have we done this already? No, because the IT response is the key. You need the neutral response. And although DE2 did have some wind measurements, really, GDC will do this in spades, I think. And I think it's a great thing.
Plus dynamic, because to get the E-region change in the winds, that's a dynamic.
Yeah, no question. And with ground-based.
No. I was just saying that really to solve this problem, we also need dynamic, because to see the E-region winds, for example, and how they change with pointing flux, we would need both missions. And ground-based, of course. I don't want to volunteer, so I don't want to hold the microphone either. Russell wants to volunteer. I see. Yeah.
I'm just going to make a comment.
I just wonder when the deadline. Oh, I'm sorry. Wonder when's the deadline for this white paper? What's the roughly timeline?
It's not announced, but they did say, Jared said this morning, I think it was, that the chairs are either announced or they're about to be announced. I guess we heard it this morning, and something like 2 months after that. So it's imminent.
Maybe it's a bit too much to put your name under any topics, but if you could put your email at least at the end, like so that we can go, if we have somebody start drafting white paper, so we could send it out. I mean, how we can just, it's great to have some working groups on those. We are here together in person, and then as we heard from Jared, and we need community, or GDC, Dynamic and Lotus need community support. And then the best way to show it is number of white papers. Right? Am I right? I'm speaking for you.
It's not just the missions, though. I mean, like, the white papers for the decadal survey should be on science as well. So we need, if this is a science topic, maybe GDC isn't going to solve all these. Maybe dynamic's not going to solve all these. Maybe we need the ground-based. Maybe we need a bunch of things. We need papers that highlight the scientific importance and what the next steps on the science. We also need papers talking about how to do it with ground-based or missions or whatever. But there might be 2 different papers, or we might have 3 different, Hide it.
I'm not sure I didn't mean to volunteer for anything. I'm not sure I quite heard what Togo said. But I just wanted to comment on that topic that, well, I was sort of intrigued by what Gong Lu said about that upward point flex doesn't necessarily mean that ionosphere is generating electromagnetic energy. I'm not sure I understood what she meant, but I do know that you can have, conversion into kinetic energy. There's also kinetic energy going on, and I know that there's been some people that, let's see, I can't remember the author, but it might be the case that sometimes kinetic energy can convert into electromagnetic energy in the ionosphere. Maybe that's what you were saying, and I'm not quite sure. I guess it can. But
the convergence divergence of the pointing flux is that's represented.
Okay, I think I probably caused lots of confusion this morning. So what I'm trying to say is that based on the Poynting theorem, it's not a directional Poynting flux is give you the energy dissipation or generation. It is divergence or convergence of the Poynting flux over a volume, space volume, that is related to energy dissipation of generation. So that's what I'm trying to say. So you cannot just think, oh, there's a downward current, downward Poynting flux, that's energy dissipation. It's not necessary. If it just goes through this volume, there's nothing happen, right? Okay, that was my point. I'm sorry, I'm confusing everybody.
So yeah, just to clear up, how does, if it's coming, if you have upward pointing flux, is there, unless you made a mistake in the measurement, it must have come from below, right? I mean.
So again, it is not necessary, right? It depends where, how you convert it. So it's a Poynting flux is three-dimensional actually, right? So you don't know where it's coming from the side. Usually you measure is from, the vertical component is usually get it. The side component you cannot get it, unless you really have a very accurate three-dimensional measurements of electric field or conductor. But usually it's not likely you will get all the direction. And also you need to measure volume. Within the volume, just not single point. You have to measure at least some spatial distance, kind of a spatial volume, finite volume, and measure everything within the volume, then you can decide. So single point does not give you any idea what is the energy, it is the energy dissipated or generated. You have to have a three-dimensional space measurements in order to get it. I know it is probably, yeah, maybe it is impossible. Yeah, I'm just strictly speaking, you have to have a whole volume measurement in order to understand. But because of the limitation, it's impossible. But you have to use maybe a combined theoretical numerical model try to infer. Yeah.
Sorry. So to come back once again, in general, I completely agree with what you said. But if you're at 600 kilometers or so, where we've never seen any major B field parallel electric fields, in that case, would you say that an upward pointing flux indicates?
I think that's exactly the point, especially when the Russell shows that there's a loss disagreement between fast measurement and the DMSP. Exactly that's the problem, because fast is in the region above or in the region of acceleration, where DMSP is a non-accelerating region. So you never know where the currents actually close and how the energy flow is going through. So at one point, 4,000 kilometers, you really cannot see how much this is actually going down to the atmosphere at all.
Okay, I think that kind of, I guess now I see the point in context a bit more, that when you're looking at fast, maybe you can't make these approximations in the same way that we can do in DMSP altitude. So that makes sense to me. Any other points? Oh, Larry?
Since the audience got quiet, I'll make my usual type of comment. No matter how many spacecraft you have, and you've got to have the spacecraft, right? You're going to be measuring things along a line at one time at every point in space where the spacecraft is. So you've got to have two dimensions as a function of time in addition. Now, obviously, you can't have spacecraft covering everywhere all the time. That's impossible. But once you've got the spacecraft, and now you get the ground base going properly with good color ASIs over a large region, which can be done, and there are proposals to do it, and you get good super-darn coverage as good as you can with higher spatial resolution, and I believe there's proposals in to do it, then you can get really good information on 2D as a function of time that you can now relate to. I mean, you can't just use the ground base and say this is what the Poynting flux is, but you say, here's a streamer, one of my favorite toys, and you can say, okay, here's what it looks like when we flew over it. Now we see this streamer coming down here, it lasted for 10 minutes and went over here. So now we got a two-dimensional information as a function of time. When we do that properly, then we really got it.
Okay, thank you. Back.
So can I make a comment?
Yeah.
I'm a spacecraft guy, and based on my experience, if we do a statistical study, it kind of can show the altitude profile of point flux, and I've actually done that for the CUSP flux tube. So it kind of resolved the issue of divergence of Poynting flux, because then statistically we can see that Poynting flux is consumed at significantly at certain altitude range. So I think maybe that's something to do. And actually, I was using polar data and thinking of doing a statistical study for the whole coverage, which really extends from 2 RE to all the way up to 9 RE. It's a sphere around the Earth, so we can really have a very good coverage and a lot of Poynting flux measurement around the Earth. And then we can see how statistically the Poynting flux is flowing, how it flows and how it's consumed at different altitudes, all the way to almost the ionosphere. And probably we can also compare to lower altitude spacecraft measurement like the MSP and FAST too.
Okay. Please put your name down if you have the a link to the page, then you can put in your email, and we'll bug for a white paper.
Okay, yeah.
Okay, if there's no more points, then I guess, oh, okay, Russell has one.
I'm hesitant to make this because it's sort of, well, anyway, I'll just say it's, I noticed, that we talk about electromagnetic things, alpha waves and whatnot when we're talking about Poynting flux. But the minute we get into the ionosphere, we stop talking about electromagnetic, we stop talking about waves, and we say it's DC. And the whole ionospheric treatment is a static treatment pretty much, or at least an electrostatic treatment. And well, underlying that, there's got to be some electromagnetic theory involved. And do we know, so the alpha wave parallel wavelength is quite long when there are no collisions. Does anybody, except me, know what happens when you start introducing collisions into the alpha wave dispersion relation? Does the wavelength, it seems to me, what I'm finding is that the wavelength shortens quite a bit. If the wavelength were to shorten so much that you actually get significant phase rotation traversing the ionosphere and coming back, then that really changes things a lot. And I think we need to know whether that could be possibly true. And because if it is, things are much more interesting. I mean, now you can have negative Poynting flux, in fact, because you've just rotated through a wavelength or a quarter wavelength or something like that. And where is that, where would that be energy even be coming from in that case? And how do you explain that? So I think that's something that needs to be looked at and understood. And I've been actually working on that and trying to get it published without success so far. So.
I think that's a great comment. I think I mentioned earlier today, there have been rocket measurements of Alfvén waves at like 200 kilometers, 300 kilometers. Ian Cohen had a paper on that. Steve Kepler also, that was on Scott Bounds' ACES. And our Royal Jets, Hassan Akbari, if you know him, he just published a paper on the Alfvén waves at 200, 300 kilometers. So I hope you can reference those as you try to explain to us how the energy is going back and forth. But I just want to say in general, again, the auroral acceleration physics emphasis of a lot of the high altitude rockets. This is the Berkeley group, Paul Kentner, Roger Arnoldy, Christina Lynch. A lot of people who are going very high up would always look at the Alfvén waves, say above 500 kilometers. And Bob Lysak would write his papers and all that. That's all great stuff. And we really haven't had that many Alfvén wave papers at the lower altitudes, mostly because these high altitude black ground 12s that go to 1,500 kilometers don't even start taking data till they're out of the, till they're 300 or 400 kilometers. And then the down leg, they're way over the Arctic Ocean where you no longer are getting data, or no longer can transmit the data. So these lower altitude rockets are suddenly opening our eyes to the Alfvén waves that are present at the lower altitudes, and they're important. And they do, and there's resonance Alfvén signatures we actually saw in CNOFs. Fernando Chimos published those. So that's at low latitude, so there's a lot going on.
Just quick, I just don't know if it's entirely relevant to what you're talking about, Russ, but Antonio Sado's done a fair bit of simulation work looking at the reflection of waves from the ionosphere as they come in. And it would be related to this change of the dispersion.
Yeah, I don't know if it's, well, the question is whether the ionosphere is being treated as a field line integrated conductance, so that, or
No,
not.
I don't think in what Antonius was doing, he treated it like that. He did actually simulate the wave packet coming in and reflecting and coming back out. So.
Okay, I've got some references. I need to go out and get these names so I can make sure I check this work. Okay, thank you.
Okay, well, it's 3:30, so I guess we'll probably call it a day and give the room back. I guess they can't force you out if you want to keep talking. Anyway, I'm going to get some coffee. Thank you, everyone, for coming, and thanks to all the speakers and the co-conveners. I appreciate it.
Just like